Okay, so hi everyone, and thank you for coming for this kind of special colloquium. So today, instead of having a regular format colloquium with an external speaker, we're going to have a lecture about, we are going to have a cycle of lectures about chosen topics in theoretical physics by members of the APC theory group. So these lectures are designed to be accessible to the poor non-theorists who are here, including myself. So today, Elias Kiritsis is going to talk about cosmology meeting fundamental physics.
Thank you very much. Let me start by saying that today I am saddened. Oops, I cannot move. Let me see if this would work. Yes. Because a colleague that most of you are too young to know, Stavros Katsanevas passed away. Apart from being a teacher and a very esteemed colleague, he was also somebody who was appreciated by the global community, and he was somebody who would also excite anybody he was talking to in physics, and he will be missed, but will be also remembered. And having said this, let me start with a disclaimer. I will try to explain the physics and new ideas in as simple manner as I can, so that it's accessible to people, who come from different disciplines. And of course, to do that, I will have to cut some corners, and therefore this is an advance warning and also an apology. Another thing I should say is that if you have a question, you can ask it during the talk, and then I'll decide as a function of the question whether I should address it immediately or move it to the end. Let me also start by describing the goal of this presentation. I will not try to solve detailed problems, but I will try to address general issues which are related to cosmology and fundamental physics. As you already know, cosmology introduces three and highlights three of the most important problems, in fact, we have in fundamental physics. The first one is the cosmological constant or dark energy problem. The second is the dark matter problem. And the third is the problem of baryogenesis. And as such, they appear as shortcomings of our theory of the fundamental forces. And this theory includes both gravity and the standard model of particle physics. And in order, at least it looks like that in order to resolve these problems, we'll have to put together, if you wish, a fundamental theory that includes all four interactions. And the difficult partner, in fact, in this sort of unification is gravity. So let me first start with a definition of what I call fundamental physics. And for this talk only, fundamental physics, it will mean the physics you can test unambiguously in the lab. And that's mostly on or near Earth. And with this definition, fundamental physics involves the standard model of particle interactions, actually almost all of it, not all of it, and nearby tests of the general relativity. The standard model of particle interactions describe three of the fundamental interactions, weak interactions, electromagnetism, and QCD, via the formalism of quantum field theory. It's a description that is in full agreement both with quantum mechanics and with special relativity. The standard model above of particle physics has been tested over a period of about 50 years, numerous experiments, different degrees of accuracy, and so far agrees fully with experiment. And its most accurate prediction, which is that of the gyromagnetic moment of the electron, agrees with experiment to an unprecedented 15 significant digits. And you see here the result, which are the quantum corrections to the number 2, which is the classical prediction of the Dirac theory, by experiment and theory. Despite this, there are reasons to change the standard model at high energies. And these reasons are that the neutrino sector we know has to be extended. The whole theory, in fact, is not ultraviolet complete. You cannot push it to arbitrarily high energy. In particular, quantum electrodynamics, and the Higgs sector. Also, there is a corner of the theory that it's difficult to calculate with, and this is QCD. The QCD of quantum chromodynamics, the interaction is strong in the infrared, and perturbation theory cannot be used. In this case, one uses numerical approaches using lattice gauge theory, and these can address qualitatively equilibrium questions. And these include, for example, the spectra of hadrons and also the thermodynamics of QCD. However, they cannot address neither scattering, non-finite density, nor off-equilibrium phenomena. Scattering in particular is calculated these days, and of course it's an important issue, semi-phenologically using various Monte Carlo programs that are tuned with experimental data. However, the finite density phase diameter of QCD is mostly unknown. And this affects, for example, the interior dynamics of neutron stars and neutron star mergers. Let me come to gravity. General relativity counts about 107 years of life and has passed many tests with flying colors. The principal equivalence, which is a cornerstone of general relativity, has been tested over a period of 100 years and is known to be valid to 15 significant digits. The self-dynamics of general relativity is harder to test because that needs strong gravity regimes. However, to date, this self-dynamics has been tested to 3 or 4 significant digits. However, several aspects of the theory, especially the ones that are related to black holes, are conceptually mysterious. Another issue is that general relativity is a classical theory, and its marriage to quantum mechanics, usually we call this quantum gravity, has created controversy for about 50 years. It is a common wisdom that quantum gravity is relevant at energies which are of the order of the Planck mass, which is a very, very high energy scale. However, this intuition is misleading. The cosmological constant problem that I will mention later on, which is a major clash between general relativity and quantum mechanics, is also an infrared problem. Let me come to cosmology. Cosmology is almost as old as general relativity. However, it has become a detailed and quantitative science more or less in the last 30 years. And it was basically affected by an impressive explosion of precise measurements. General relativity is one of the theories that go into cosmology, but it's not the only one. Many other aspects of cosmology rely on the standard model of the particle interactions, as well as disciplines like statistical mechanics, thermodynamics, and fluid mechanics. And it's fair to say that today, most of the input we have about new physics now, for once, comes from cosmology. One very important ingredient of early universe cosmology is inflation. Now, inflation is a paradigm. It was proposed in 1980 by Casanas and then Guth, and it has become one of the pillars, in fact, of the modern cosmological framework. It was proposed originally to solve 2 conceptual problems. One is called the horizon problem, and the other the curvature problem. The curvature problem is the fact that if you want today to have a universe that is almost spatially flat, as we observe, you have to fine-tune the curvature. If you go back in time, at the beginning of time, let's say at the Planck time, to 60 digits. And this is very curious. That's the curvature problem. The horizon problem is that we look at the primordial universe by looking, for example, at the CMB. We find that the CMB is homogeneous wherever you look. It has the same temperature, and the inhomogeneities are tiny. They're 10 to the minus 5. So, on the other hand, if you look in the sky and you ask what parts of the sky could have talked to each other in the past, according to the standard evolution that we know about the universe, the answer is about 2 degrees, a tiny part of the sky. And the question is, how is it possible that things that cannot communicate can have the same temperature? That's the horizon problem. The major, of course, inflation was proposed to solve these two problems, and it does. However, its major breakthrough was that it predicted something that was unexpected. It predicted an almost scale invariant and almost Gaussian spectrum of quantum fluctuations, which are responsible for the observable structure of the universe today. And the enormous, in fact, progress in observation has made this idea more than plausible. In fact, today we do consider that these original quantum fluctuations are the seeds of the structure we see in the universe. Let me now simplify just to get the idea behind inflation. Let's consider a theory, a gravitational theory, with a positive cosmological constant. Here is the Einstein action, and here is the cosmological constant. This is the Planck mass. Now, if you solve the equations of this gravitational theory, the most symmetric solution is known as the Sitter space. You have all seen the metrics of this space. These are the most common coordinates known as Poincaré coordinates. And it's basically, if you look at this coordinates, it's a flat three-dimensional Euclidean space, that space, which is exponentially, its length scale is exponentially expanding in time. So because it's exponentially expanding, that's why we call the time period where this happens, in fact, inflation. The speed h of this exponential expansion by the equations of motion is related to the cosmological constant via the well-known formula. Now, this expansion is superluminal because if you take a length scale, it's the scale factor times a length that doesn't change according to the metric, and you compute now the velocity, the L over dt, you do the differentiation, you rewrite it in terms of L, and then you find that it is h, which is a constant times L. And in fact, for L large enough, this is bigger than 1. So V is bigger than 1, and 1 is my speed of light. So everything is normalized so that the speed of light is 1. Therefore, most of the velocities that you will find, especially if you go far, you look at large distances, are superluminal. And therefore, the horizon radius, which in Minkowski space increases linearly with time, here it increases exponentially fast. And because of this, all the regions of space become eventually causally connected. In fact, the Sitter space does not have neither a curvature nor a horizon problem. It solves both problems. The other thing that you can observe from the metric I wrote here is now you go to time minus infinity, this scale factor goes to 0. It's like normal space shrinks to 0. And that looks a little bit like usually what we call the Big Bang initial singularity. But this is an impression, and it's not true. In fact, in the Sitter space, there is no singularity at all anywhere. It's a regular space, and in fact, what you get at t equals minus infinity is a past horizon, because the coordinate system is not very good, and the space-time is perfectly regular, in fact, at the beginning of Poincaré time. And to see this, you have to write it in better coordinates. And in these coordinates, which are not global coordinates, the same space has a metric, which is time. This is the metric of a three-sphere, and this is a scale factor that changes with time as a cos square. And if time goes like this metric is describing a three-sphere whose size goes to infinity in the past, goes down to minimum, which is equal to the length scale, which is h, and then goes all the way to infinity in the future, and it's a perfectly regular space. Like Minkowski space, the Sitter space has a very large symmetry. And the most important part of the symmetry, in fact, is scale invariance. And this scale invariance plays a central role in the inflationary theory. So how do you make inflationary models? Well, essentially, you have to realize a period during the evolution of the universe when the space-time is nearly described by the Sitter metric. And according to what you said, in order to do that, you have to have a period in the universe where the only energy density behaves like a cosmological constant, like a vacuum energy. So that means that you need all the other kinetic energies to be small. For example, suppose you have a scalar field, you have a potential, let's say like this, that you can immediately get by putting the scalar field to sit here. It will stay there, it will not move, zero kinetic energy, it will have only the energy at the bottom, and this is a cosmological constant. So in that case, you'll get de Sitter space. The only problem with that is that you will get de Sitter space for the whole period of the universe, and that's not what we want. To get a de Sitter space for a piece of the history, you need to do more. You have to get more complicated potential so that for a certain period, the field is moving, but it's moving very slowly. And in order for this to happen, your potential must be almost flat. And then it is moving slowly, it has very small kinetic energy, and then the potential energy more or less will drive the exponential expansion, and the geometry will be near the center. And in fact, it is precisely such a period that we call primordial inflation. Now, eventually, of course, the scalar will roll and it will arrive at a place where the potential is steeper. And then what you expect is that then it will roll back down, maybe it will oscillate here. And then the energy that it had here, more or less, which was inflating the universe, now it will be transferred to other types of matter that are coupled with the scalar field that we usually call the inflaton. And this is what we call reheating, passing this energy, which is vacuum energy, now to other fields and create particles. So any scalar with the right potential could do the job. But this scalar doesn't even need to be fundamental. It can be a bound state. In fact, in the standard model, we have bound states, the pions. Unfortunately, they don't have the right potential to do that. But it can be an even more exotic scalar. For example, it can come from the scalar curvature of space itself. And the scalar coming from the scalar curvature is known, in fact, in cosmology as the scalar. And one of the most famous models of inflation, which is the Starobinsky model, is described precisely only with curvature. This is the usual Einstein term and the standard Einstein gravity with the Planck scale. And then you add an R squared term to it with a coefficient which is dimensionless now. And to get the right numbers compared to what we measure, this coefficient has to be negative and of order 10 to the 5. And in this case, basically, it's this R squared term that generates a scalar mode. And if you plot the effective potential for the scalar mode, indeed, it looks something like this. This paradigm of inflation can be realized, in fact, by an infinity of models, as you can imagine. There are literally thousands of different models in the literature. And even in the case of a single scalar field, you can imagine many different potentials that can do the job and which agree with data constraints. But there are many more realizations that utilize more than one scalar. For example, you can utilize several scalars, but you can even utilize things which are not directly related to scalars, like what is known as Kusawa-Lifshitz gravity, brane universe inflation, Mirage inflation, ectotic evolution, etc. And the question, of course, here is how do we classify and categorize models of inflation? And the idea here is that one can use the symmetry, and the Sitter space has a very large symmetry. Its four-dimensional de Sitter space has O1,4 symmetry. And apart from being the symmetry of 4 plus 1 dimensional Minkowski space, it is also known to be the symmetry of 3-dimensional Euclidean quantum field theories that are scale invariant. And then you can use quantum field theory techniques that we know, in fact, how to use to classify inflation in 3 classes. And this is what we have done with Pierre Benetry and his students some time ago. However, it is important to understand that in order to have early universe inflation, you always have to fine-tune the theory. Let's understand why. Here I wrote the Hubble evolution equation. This is the Hubble scale, which is time dependent, of course. This is the density of radiation. This is the density of non-relativistic matter. This is the curvature of space if it's there, and this is a cosmological constant. And it's clear that if you go to late times in which A goes to infinity, all of these terms go to zero, and the cosmological constant wins. Therefore, if you want late time inflation, that's easy. And this is, of course, the case with dark energy. However, if you want to have inflation as A goes to zero, that is, you go in the past, as you can tell, all of these terms become very large, and you have to really tune your theory to be able to get rid of them. However, the most challenging problem of fine-tuning in order to have primordial inflation is the fact that in general, you expect quantum gravity fluctuations. These, of course, will happen at the characteristic length of gravity, which is the Planck length. And these fluctuations, in fact, create inhomogeneities that don't let inflation stop. And also, there is something related to this that we should remember. What we usually call the Big Bang now in inflationary theory is essentially the end of inflation. It's essentially the reheating of the universe. And the important question, of course, which so far we cannot answer here, is how did inflation start? And a related question one can ask is whether we can ask and answer questions that pertain to before inflation started. We don't know. Let me mention another problem that exists, but it's not well known. Now, when you consider the theory of an inflaton, you treat it semi-classically or as a weakly coupled theory, and the leading quantum corrections, which lead to the spectrum of perturbations, are well controlled. These have been computed since the early 80s, and these are the basis for what we now call the theory of perturbations that give rise, that we measure in the CMB. The interactions, in fact, in that theory are very weak. And this is why non-Gaussian are small and so difficult to measure. And until today, we haven't seen them. However, people have studied quantum field theories in the zeta space, and they found that quantum corrections, although small, produce logs that depend on time. And of course, for small periods of time, the logs are small, but if you wait long enough, these small corrections become large and they invalidate perturbation theory. So quantum perturbation theory is problematic in the zeta. There are some techniques due to Starobinsky to resum some of these corrections, but they are not sufficient to control the full perturbation theory. And this problem affects, in fact, all perturbative theories, and its resolution is not yet known. And in fact, whether what we compute in perturbation theory to leading order, for example, is reliable. Another important question is to what extent you can embed inflation in fundamental theory. The simplest possible context, in fact, is what is known these days as Higgsflation, in which the inflaton is the Higgs. Now, the obvious advantage, of course, is you're using a particle you know it exists. But there are disadvantages, unfortunately. First of all, the Higgs potential, as we know it, and more or less we know it, is not a good inflation potential. And moreover, all the other problems I mentioned basically affect Higgs inflation. And to make it work, you have to add a new term. This term, so here is the kinetic term of the Higgs, here is potential, here is the Einstein term, and you have to add a term which contains the scalar curvature and the Higgs square with a dimensionless coefficient, which is quite large. And what this does, it lowers the cutoff of the theory, which goes down from the M-Planck scale. And in fact, at the place where you want to do the inflation, you cannot trust anymore the theory. However, this you can fix. If you add also Starobinsky's R-square term together, then you can make a theory that works and at least can reproduce the data of what we see today. Let me now come to dark energy. As you all know, today's cosmological observations indicate an acceleration of the universe, and this corresponds to an acceleration rate, or Hubble constant, which is in high energy units, electron volt, 10⁻⁵. So this indicates we're entering a new future asymptotic region of de Sitter space. This is very similar to area inflation. The only difference is now that this h divided by the Planck scale to make a dimensionless number is 10 to the minus 31 and not 10 to the minus 5 that we have for early universe inflation. Again, like in the past, in this case, there will be nearly scale invariant fluctuations that will be produced, but now they will be tiny. The other thing that is, in fact, interesting is that if you ask what kind of vacuum energy is responsible for this late time acceleration, you must have m squared times lambda to be 10 to the minus 3 to the fourth, and therefore the cosmological constant divided by the Planck scale to make something dimensionless is this enormously small number, 10 to the minus 124. That's what we measure via gravity, of course. The problem with this is that this measurement of the vacuum energy is in gross disagreement with quantum field theory calculations. In fact, you all know that quantum mechanics gives always a non-zero energy for the ground state, and this is known already from the simplest example, in fact, we studied in quantum mechanics, which is the harmonic oscillator. You know that the energies of the harmonic oscillator are given by that formula. If you take the ground state, you get a positive energy, although the minimum of the potential is at zero. On the other hand, nearly free quantum field theory is a collection of an infinite number of harmonic oscillators, and therefore we naively expect to have in a quantum field theory an infinite vacuum energy. However, as you all also know, you have to do renormalization, and when we do renormalization, this vacuum energy is finite and gives rise to what is known as the Casimir force. The Casimir force is not easy to measure, but it was first measured by Lamoureux in Los Angeles for the first time in 1997. And since then, many experiments, in fact, have shown that quantum field theory predictions for the Casimir energy, that is the vacuum energy, agree with the Casimir force that is measured at the level of 1%. Moreover, we know from theory that if you have a degree of freedom at the mass scale m, this contributes to the quantum vacuum energy with a term that's proportional to m to the fourth. Now, in our theory, the largest known scale, in fact, that appears is the Planck scale. And therefore, in quantum field theory, you would expect that lambda should be of the order of m Planck squared. And then that would make lambda over m Planck squared to be of order 1. And this number is 120 orders of magnitude wrong, or at least in disagreement with experiment. Of course, you may think ways out of it. For example, we know that bosons and fermions give opposite sign contributions to the vacuum energy. And then if you have a symmetry that somehow tell us that there are cancellations between bosons and fermions, like supersymmetry, you can use this, in fact, to make these contributions vanish. However, the problem is that such a symmetry, we know, is not valid below the energies we measure. And we measure more or less up to 1 TeV. So you can fantasize that this symmetry exists above 1 TeV, and then the best you can do for the ratio of lambda over mp squared coming from quantum field theory now has 1 TeV here, and it's 10 to the minus 64. It's still different by 64 orders of magnitude. And of course, what you suspect is either the gravitational interaction must be modified, or how quantum field theory coupled to gravity must be modified, or both. Most physicists feel that the key is in the marriage of general relativity, which is a classical theory, to quantum mechanics. Now, general relativity is very different from the other three fundamental interactions when it comes to quantum effects. And it is something that we call non-renormalizable. And its simple explanation, it means that the classical theory, GR as we know it, cannot tell us what is the nature of the quantum theory, unlike the other three interactions. And after efforts that span more than 70 years, the only examples of a quantized gravitational theory we have with a semi-classical limit are those that are included in the framework of string theory. But they can only address weak quantum gravitational effects. And of course, in that context, the quantization of gravity comes at a cost. You have to introduce a new scale, which is below the Planck scale and is known as the string scale. Before going further, I will make a detour, which a priori, it's not obvious why, but you will see it later. You all know that hydrodynamics, which means the Navier-Stokes equations, and the associated equilibrium theory, which is thermodynamics, are considered the dirtiest version of fundamental theory, of physical theories. And certainly we cannot call them a fundamental theory. However, the flip side of this is that at the same time, they are the most generally applicable physical frameworks, because more or less any quantum mechanical microscopic theory has an effective low energy, low wavelength description in terms of thermodynamics and fluid mechanics. Of course, this description needs a few parameters, which are usually you put them by hand or you measure them, but in principle, you can calculate them if you knew what was the underlying macroscopic quantum theory of the material. And this applies more or less anywhere, except if we're very close to the ground state or vacuum of a theory. There's something similar, or at least something that looks similar in gravity. As you probably know, when you study black holes in general relativity, it has been found in the 70s, and to the surprise of all, that they follow the laws of thermodynamics. And eventually, that was extended, in fact, to the rest of gravitational physics in later decades by Jacobson. Moreover, in 1978, in a prescient paper, Imogabur had shown that if one moves a little bit out of gravitational equilibrium, then the long wavelength dynamics of the gravitational field is described by the relativistic Navier-Stokes equations. At the time, nobody paid attention because the responses he got were negative, and this didn't make physical sense. What I would like to do now is to pass to another theory that has the same problems as gravitational theory when you would like to make it a quantum theory. That's a well-known theory. It is the low energy theory of the strong interactions. The lightest particles, in fact, in the strong interactions are the pions. The low energy theory of the pions is a very symmetric theory, which is known since the 60s, and it's given by the famous chiral Lagrangian. It is written here, the dynamical variable is an SU2 matrix, which defines via the standard formula the three pions. Pi A, 1, 2, 3 are the pions. And then this is, of course, depends on space and time. You put it and you construct this trace, that's the kinetic term. It's fully nonlinear, as you see in terms of the pions, because of the exponential. This is a mass term, but it's not important. And then it contains a mass scale, which is the famous F pi square in front, and that controls the interactions. It has many similarities with general relativity. Both theories have a single mass scale, this F pi, plays the role exactly of M pi, and of the Planck scale, which is sitting in front of the Einstein action. And it is this scale in both cases that controls the infinite number of nonlinear interactions that both theories have. If you forget the mass of the pions, in that case, the pions are massless, and one theory describes spin 0 massless pions, and the other describes a spin 2 particle, which is also massless. And both theories are non-normalizable and infrared free. Interactions become weaker as you go to low energy. Now, in the 60s and 70s, physicists of the strong interactions tried to compute quantum effects for the chiral Lagrangian, and they realized that the infinities could not be controlled, that for each new Feynman diagram, you had to add more and more new terms in the chiral Lagrangian, etc. That's what it means, in fact, that the theory is non-normalizable, and the quantum theory essentially doesn't make sense beyond energies of order this scale, F pi. At higher energies, the interaction becomes stronger, theory is non-unitary. So the quantum theory, the conclusion was that the quantum theory of the Lagrangian can describe the strong interaction physics only below F pi. It's an incomplete quantum theory. And of course, it remained as a puzzle at the time, what's the full quantum theory of measures? But today, of course, we know the answer to that question. And the answer is that the fundamental theory of the strong interactions is an energy 3 gauge theory with basic fields, gluons, and quarks. The gauge interactions of that theory are very weak in ultraviolet, that's the famous atomic freedom, and therefore at high energy quarks and gluons interact weakly, but the gauge interaction becomes strong at low energy, and quarks and gluon bind in colorless bound states. And these are the mesons, baryons, and gluons that we see in the experiments. The mesons are the lightest bound states, and their effective in theory is precisely the Lagrangian. Therefore, the pions are composites of the fundamental degrees of freedom of QCD. And they are composites that are strongly coupled, and one, by analogy, would suggest that the non-normalizability of the graviton appears because it's a composite object. That is, the graviton is a low energy bound state. So how could you generate a graviton that's a bound state in a quantum field theory? There is a unique, in fact, a natural state in a quantum field theory that would play that role. And this is the state that generated out of the QFT vacuum by a very special operator, which is the conserved energy momentum tensor. It has exactly the quantum numbers of the graviton, and it generates a state when it acts. This is the energy momentum tensor. It acts on the vacuum of the theory, and it gives a special state which would behave, at least as far as quantum numbers are concerned, like a graviton. It is transverse as the graviton is because of energy conservation, and one can make it traceless. In fact, if you are in a weakly coupled theory, you construct such a state. In fact, this is a multiparticle state. And therefore, if you try to find what are its interactions, in fact, this would be completely non-local. However, if you assume that you are in a theory which has strong interactions, and therefore this state is truly tightly bound state, and let's say it has a size capital L, then maybe you would hope that if you look at distances much bigger than L, maybe this would reproduce gravity. And in particular, if you take the limit of infinitely strong interactions, you would expect to obtain a good point-like interaction theory for this bound state gravity. If the quantum field theory is massive, this bound state gravity would be massive, but if the theory is scale invariant and massless, such states usually form a continuum starting from zero. And this is the case of the famous ADS-CFT correspondence, where this idea essentially was taken from. In fact, the ADS-CFT correspondence relates quantum field theories to string theories. So string theories, on the other hand, we know are theories of quantum gravity, so therefore it relates quantum field theories without gravity to theories where gravity is dynamic and quantum. And the original example is a duality or equivalence between two completely different objects. On one hand, you have a D equal 4, four-dimensional SUN supersymmetric Young-Mills theory. That's a very symmetric cousin of the usual Young-Mills theory we have. And this contains gluons and their partners. And this theory is equivalent to a 10-dimensional string theory, which is moving in a very symmetric Kent space. It has a space which is a de Sitter 5-dimensional space, constant negative curvature in 5 dimensions, and the sphere in 5 dimensions, which is constant positive curvature in 5 dimensions. Now, when we take the number of curves here to go to infinity, the string theory is weakly coupled. And when the coupling constant of the Young-Mills theory lambda is very strong, then this string, the dual string, is very stiff. You can neglect its vibrations, and then the theory, the string theory, can be approximated by a generalized gravitational theory. The picture of the de Sitter space is like this. You have 5 dimensions. It has a boundary. It has an end of space, which is a finite distance. This is the end of space. It's 4-dimensional Minkowski space. That's where the quantum field theory lives. And it has a 5th dimension where, in this bigger space inside, the string theory lives. And the two, in fact, are two equivalent descriptions of the same thing. One contains gravity, the other does not. So this holographic duality essentially implements what we discussed already. The graviton and all the other bulk fields, in fact, that circulate in 5 dimensions are composites of the gluons of the quantum field theory. And the quantum field theory is strongly coupled, as expected, and this is important in making the gravitational theory local. And together with gravity, of course, you obtain an extra dimension, which is infinite in size, the 5th dimension. So what we learn from Elias CFT is that strong coupling in a quantum field theory would make the gravitons that appear there tightly bound states, and large N makes these gravitons interact weakly. And both the above, in fact, will give us eventually an effective semi-classic theory of composite quantum gravity. Now, this gravitational action we get is ubiquitous. Any theory which has large N strongly coupled will give you some gravitational theory, not necessarily the same. This indicates that the gravitational interaction is not fundamental. It's an average low energy theory of bound states of different QFTs with many degrees of freedom. And in this, it is very much the analog of what we have in fluid dynamics and thermodynamics. Different fundamental degrees of freedom eventually at low energy look like fluid dynamics. And this explains also why the appearance of thermodynamics and entropy in gravity is natural. In particular, in this correspondence, which is known as the holographic correspondence between gravitational or string theories and standard quantum field theories without gravity, Einstein-de-Sitter black holes describe the finite temperature canonical ensemble of the dual quantum field theory. So the idea of emergent gravity that I described says that in any quantum field theory, which is defined on a fixed background metric, let's say it's Minkowski metric, it doesn't fluctuate, it's not dynamical at all. It will give rise, on the other hand, to a theory of spin-2 transverse fields, which I will call them generalized gravity. And if you want to say, what is this metric, which is dynamical? Well, it is the expectation value of the stress tensor in the quantum field theory. And we know in quantum field theory how to construct the quantum effective action of the stress tensor. And in fact, it is a function gamma of this expectation value. And the formula for how you construct it is well known. And the variation of this being 0 is the generalized Einstein equation that you will obtain, in fact, for this gravitational theory. Now, for any QFT you do that, you will get a general coordinate invariant theory if the original quantum field theory is translationally invariant. And if the quantum field theory is generic, then this particular gamma you will construct, of course, will describe a theory that has a spin-2 particle, but doesn't look like normal gravity. However, if the quantum field theory is holographic, and this means strongly coupled, large number of degrees of freedom, and few low-dimension operators, then this gamma describes a semi-classical, weakly coupled generalized gravity theory where the Planck scale is proportional to the number of degrees of freedom and therefore is large. And this gravitational theory contains always more fields at the metric, and one that's universal, it's always there, is the dilaton. And the dilaton is the trace of the energy momentum tensor. This field, when it's there, generically violates the equivalence principle of this gravity theory, and it can be invisible only in some regimes, depending on the dynamics. Let me, how much time do I have? Let me come now to another issue, which is to a certain degree unexpected. That is, there is a direct connection between what we call quantum entanglement in quantum mechanical theories and semi-classical gravity in the way that we constructed it. First of all, we know that the entropy in gravity is encoded with geometry. In this special example of black holes, basically entropy equals horizon area. a geometrical object. We now, on the other hand, understand much more than this. We understand that the whole fabric of space and time, that is how a manifold is constructed, in fact, from the fundamental degrees of freedom, and the fundamental degrees of freedom now are, if you wish, the quarks and gluons, are the fields whose bound state is the ground. The way that this, in fact, is constructed has to do, as I already argued, strong interactions, but also strong quantum entanglement. Already we have a famous formula due to Ryo Takayanagi, which computes quantum entanglement entropy from geometry, but I think it is a little bit more easy to understand the following example. You all know the Schwarzschild solution, and the Schwarzschild solution, in fact, this is the Penrose, this is known as the extended Penrose diagram of the Schwarzschild solution. The usual region, which is outside the horizon is here, is region 1. This is infinity, and this is the horizon. And when you move like this. Now, if you want to go inside the horizon, you all know that you have to change coordinates. You have to go to Eddington-Filkestein coordinates so that the horizon is not singular, and then you get region 3. Region 3 is the region inside the horizon, and here is the singularity. That's usually what you get. However, it is known since the 60s, and that was done by Kruskal and Sekeres, that there is another set of coordinates called Kruskal-Sekeres coordinates, in which you can see other parts of this geometrical space, which are parts 2 and 4. Now, this is unusual because part 2 has another asymptotic region, and this asymptotic region, this infinity, if you wish, has nothing to do with that. It's different. Moreover, you cannot communicate from here to here. This was a mathematical curiosity for more than 60 years. And in fact, if you look at the geometry at the slice at t equals 0, it looks like a wormhole. This is one asymptotic space, this is the other, and it looks like this. And in fact, this is the horizon here. That's a simple calculation, in fact, that usually people do in GR classes. Now, let's see what this means in view of what we said. In fact, the extended black hole solution corresponds to a pure state, which is known as the thermofield stable state, in a product of two quantum field theories. According to holography, for every asymptotic region, we have a quantum field theory. So here we have two asymptotic regions, so we have two quantum field theories. They are the same because this is similar to this. So let me call this quantum field theory that's sitting here right, and this left. These are not interacting, and in the Hilbert space, I can make this statement. Take energy eigenstates of one theory, tensor them with energy eigenstate, the same energy eigenstate in the other theory, and sum over them with some coefficients, which have to do with the energy. Now, this is a linear combination. It's known, it's a pure state in the product of the two theories, which are completely distinct. It's known as a thermofield double. And in fact, of course, this is a state in which these two theories are entangled because it's a sum of products of states of the two theories. The claim is, and there are good reasons why this is correct, that this state, that basically this formula, I write it like this, is exactly the connected geometry I showed you before. What this shows is that entanglement in the underlying quantum field theories, underlying the gravity, can be used, in fact, to stick together things in geometry that otherwise are foreign to each other. And that's why we believe, this is of course one of many examples, we believe that entanglement is an important way that keeps manifolds together in gravity. Now, there is one more calculation one can do. If you have something like this, from the point of view of one theory, you can trace out the other theory because, let's say, you don't observe it. Everybody knows that in that case, you generically get a mixed state, which has a density matrix, and this is a textbook calculation. And if you do this calculation, you'll get a density matrix that looks like this. And this is the thermal density matrix of the right theory. And this density matrix, when we're doing the tracing, is describing these two pieces, which, as we know from the work of Hawking in '74, are described precisely by this thermal density matrix, where T is the Hawking temperature.
So here you say they describe regions 1 and 2, and you pointed to 1 and 3.
I said 1 and they describe, sorry, which describes, you mean this?
No, I said your last point.
No, this is wrong. In fact, I'm sorry, thank you for mentioning it. This is 1 and 3. These are the standard two regions that we usually study when we have this solution. Thank you. Let me get back now to the cosmological constant problem. From the properties of the major nature of gravity as we described it, in fact, one can show something which is quite general. Suppose you take your microscopic theory, your quantum field theory, which generates the gravity, to be defined on a space with flat metric, nothing simple, so this is the Minkowski metric. Then you can prove quite generally that the flat metric always solves the emergent gravitational equation independent of quantum corrections. It doesn't matter what the quantum correction is. Flat metric is always a solution to the gravitational equations. Now, this is in contrast and very different to what you have in standard gravity. You take standard gravity coupled to the PFT, PFT generates a cosmological constant, and then, of course, if you have a cosmological constant and you try to solve the gravitational equations, the flat metric is not a solution. Now, of course, this fact does not really solve the cosmological constant problem, but it makes it much more manageable. In fact, we can realize what is the gravitational picture of this statement that can be proven, in fact, in quantum field theory, and this is known, in fact, in the gravitational context as the self-tuning of the gravitational constant, and let me describe that now. So, how do you make the standard model of particle interactions, the three interactions we have, coupled to gravity in the way I described? So, you have two options. Either you take a three-dimensional holographic quantum field theory. Now, we know that the three-dimensional holographic quantum field theory would generate a four-dimensional gravity, according to what we said, and then you take this four-dimensional gravity and you couple it to the four-dimensional standard model, the other three interactions. Now, that's a possibility, but nobody has been able, in fact, really so far to realize it. So it remains an unknown whether this can be done. However, what we can do is to start from a four-dimensional holographic quantum field theory that will generate gravity. This will generate now five-dimensional gravity, and then I can couple this five-dimensional gravity to the four-dimensional standard model. And in fact, this has a geometrical picture, which I will now show. So your four-dimensional quantum field theory with many degrees of freedom that will generate gravity. So this is fifth dimension, this is four-dimensional Minkowski space, this is the boundary of this five-dimensional space. That's where my generating, if you wish, quantum field theory is sitting. And it generates this five-dimensional gravity. And maybe other fields together, like the dilaton, etc. And now, in there, I have to put my four-dimensional quantum field theory, which describes the quarks and gluons and the leptons and the Higgs, etc. And this, since it's four-dimensional, is like a four-dimensional 3+1 dimensional submanifold that is sitting somewhere in the interior. And the picture is a little bit like this. It's like a brain, a 3+1 dimensional brain, sitting in a five-dimensional space. This is the geometrical picture of how we describe the four-dimensional quantum field theory generates gravity, which is now five-dimensional, coupled to the other interactions, which are four-dimensional. Now, these are known as brane modes, and they have been motivated by deep branes in string theory and have been studied extensively, in fact, 20 years ago. And in fact, in that context, we can show in general that, first of all, gravity as felt by the inhabitants of the standard model brain, that is, we are made by hadrons and leptons, etc. We are sitting on the brain. We cannot go in the back. And we can ask the question, what kind of gravity do we feel on the brain? Is it 5-dimensional? Is it 4-dimensional? How does it work? And in fact, you can show that at least in some large range of scales, this gravity is 4-dimensional, not 5-dimensional. That's important because what we observe in this world is 4-dimensional gravity, not 5-dimensional gravity, at least where we look. The next thing you can show is that even if the cosmological constant on the brain, because that's the only cosmological constant we're sure of, because it comes from the quantum effects of the standard model fields, if this cosmological constant in the brain is large, there is always a gravitational solution where the metric of the brain, that is the metric we feel, is large. And this is the analog of the statement I made before. And this is what we call the self-tuning cosmological constant. That is, all the fields in this 5-dimensional space adjust so that the effects of this cosmological constant in the brain, instead of curving the brain metric, curve the body. Now, this happens when the standard model brain, you don't put it anywhere. It's a very special position in the bulk. And if you change this cosmological constant, this position will change. So in this context, how do you do cosmology? And in fact, you could call cosmology in this context brain cosmology. So the cosmology in this context is in fact correlated with the motion of this brain in the 5-dimensional bulk. This, to solve the equations for its motion, is a technically highly non-trivial problem. However, there are a few cases and a few simplifications where one can do things. For example, if you treat this standard model brain as a probe in the black geometry, it means that it moves as the geometry tells it, but it doesn't back react to the geometry, then the problem is solvable. And it seems that one can accommodate in this context both early inflation and a small late time cosmological constant. In particular, the self-tuning point of the static standard model brain is precisely the minimum of an effective potential. And this is the notion of self-tuning. It's like the place where you put the brain and it stays there without any cosmological constant. But of course, this is not enough. There are periods where the probe approximation is invalid and more effort is needed to solve this problem. So let me come to conclusions. I argued that quantum gravity is a generic effective theory of strongly coupled quantum field theories with many degrees of freedom. The microscopic nature of the degrees of freedom is visible only at very small distances. The degrees of freedom explain both the non-normalizability of the effective gravitational theory and many of its other peculiar properties. The fabric of space and time is intimately related to the entanglement properties of these underlying quantum entanglement properties of these underlying degrees of freedom. And this picture has many implications for both cosmology and the rest of fundamental physics. Now, many some implications remain to be worked out, and many also problems remain to be solved. This is not a finished topic. However, it's not clear how to experimentally test these ideas, because most of the time, if we go in gravity, they would require difficult places where to do measurements. However, recently, we had some confirmation from a completely different viewpoint, because there are other theories that generate the effective gravitational theory, if you wish, which doesn't look like the gravity which is outside, but which we have studied. And we have seen, in fact, several of these things realized. And in fact, the experiments are heavy ion collision, and the gravity one observes there is not usual gravity, is an effective gravity that appears in QCD. And in fact, one thing that can say with simple words is that when you make these collisions, what you create is a black hole, a microscopic black hole in this very peculiar gravitational theory that describes QCD. And that's why we know, at least from experiment, indirectly, that some of these things are not complete science fiction. Thank you.
Okay, thank you very much for this very clear and exciting lecture. Other questions? Okay, so I have one small question, which is, so you mentioned like QCD in the context of this, just to illustrate kind of this idea-CFT duality. So is n equals 3 large enough?
Not enough in order to have exactly all of this, but apparently from what we know, in fact, from Lattice calculations, enough to at least see some of these hints. In fact, there are some famous Lattice calculations that calculate the thermodynamics of Yang-Mills for n equals 3, 5, 6, 8, up to infinity. And the difference in that particular case is only 5%. Now, the gravity you get is not gravity with massless gravitons, because the graviton in Yang-Mills is known, which is a spin 2 plus blue ball, has a mass of about 2 GeV, 1.7 GeV. But at high enough energy, this mass is not important. And that's why we understand, and of course, eventually the way we analyze the data show that at very high energy, you can still describe what is created as a black hole in this peculiar theory, because precisely we are far away from this massless limit.
Okay, thank you. Yes.
So I have a comment and a question. So you mentioned the analogy between the chiral Lagrangian and gravity. Of course, there is a big difference, because in the chiral Lagrangian, even for for massless pions are scalars, whereas the graviton is a massless spin 2 particle. And there is a theorem that you cannot have in 4-dimensional Lorentz invariant theories a massless spin 2 bound state.
That's true.
So what works for the pion naively doesn't work for the graviton, right?
That's right.
So
and
is there any way around this that people have sort of come up with, except for holography? Like,
well,
holography works because it's gravity in a higher dimension.
Francesco is referring to the Witten-Weinberg theorem, which is a theorem proved in the 70s, precisely because people even at the time tried to do that. This is a theorem which says that if you have a quantum field theory without gravity, that has Lorentz invariant, in fact, independent of gravity, that has Lorentz invariance and a Lorentz covariant energy momentum tensor, then in the case we are interested, for particles, for example, with spin 2, which is what we're interested, that they cannot be massless. And of course, this theorem has various loopholes, which I don't know, probably if you have them. The first is, of course, that if you take a graviton you couple to that theory, this avoids the theorem. And the reason it avoids the theorem is that if you put a graviton, the momentum tensor is not conserved. However, there are other loopholes. So to make the long story short, what is allowed by the theorem is, without, let's say, fundamental gravity, is either a continuum down to zero mass, and that's how conformal theories do it, or a mass gap and a massive gravity. So that's what's allowed. But as we know very well, a continuum down to zero, and then the DGP mechanism is enough to make the job.
A continuum down to zero in the case of the CFT, you can also read it as a higher dimensional theory. This is what holography.
Right, but on the other hand, when you correct this for the DGP mechanism, then some of these, when you are in the 4-dimensional regime, these will be different. There will be subleading corrections, whereas if you are in 5-dimensional regime, they will be there in your face.
Are there other questions? Yes.
I have a very short one. So on your, I think it was the last slide before the conclusion of the brain cosmology. So you were mentioning that so that you can accommodate both early inflation and small late time cosmological constant. So my question is, what is then the cosmological constant? I mean, in all of this, how should I interpret the cosmological constant?
The cosmological constant will not be a cosmological constant. In fact, if you really go to the bottom of the potential, the cosmological constant is zero. What you will have is the cosmological constant would be a slow roll without a cosmological constant. So that's what's expected. If the initial conditions on your universe brain were to put it at the minimum, there would be zero cosmological constant and the space would be flat and nothing would happen. But this in fact needs to be worked out the details. But what we know is that if the brain just moves without any density, so without exchanging energy with the bulk, then we go to the minimum, we start oscillating. Of course, that's not what the universe is doing. We expect that the interaction with whatever is on the brain and possibly bulk brain interactions will give you this sort of friction, which you will asymptote to the minimum, and during the when you asymptote, you will have this acceleration. That needs to be worked out.
Yes.
Yes.
Giovanni?
Yes, thank you very much for this nice seminar. On the last bullet of the last slide, can you provide a bit more details about the measurements that would corroborate or?
In fact, 6 years ago, I gave a colloquium on that, which, if you're interested, I can send you the file. But let me say a few words. Heavy ion collisions are collisions with ions, which are, in fact, in the past, they were done in Stony Brook, now they're done at CERN. Alice is the experiment that measures this, but now all the experiments are measuring this. You accelerate them to very, very high energy to collide them. They have enormous energy, which, when they collide, is deposited on one place and generates billions of quarks and gluons in a soup that very soon thermalizes, and it is in a phase in young males that in QCD, which is known as quark-gluon plasma. It's a different phase from the usual confined phase. It has been studied for the past 20 years in the day from such experiments, and then this ball of matter has temperature which is about 10 GeV in high energy units. The transition is at about 1 GeV. This is GeV per cube. And then it starts expanding, of course, because it's in the vacuum. It starts expanding as temperature goes down. And when the temperature reaches 1 GeV per Fermi cube, across the phase transition, all of this soup becomes now hadrons, which eventually fly off to the detectors, and they're minor. So that's what we have good reasons to believe it happens. Now, in a theory, if QCD was close, in fact, to holographic theory, the same picture is you have a big blob which looks like a black hole, which is in a space that looks a little bit like other de Sitter. It's not exactly the de Sitter because this is not a scale invariant theory, but it has a boundary, and this black hole is falling inside an de Sitter. And this is what the expansion looks like if you see it in 5 dimensions. And then eventually, when it starts reaching the bottom, it evaporates via Hawking radiation. And that's what you see in the detectors. Not only that, in fact, one can use techniques from black holes to estimate even the multiplicity that one gets from collisions, very high energy proton collisions, which have very high multiplicity. And these estimates more or less agree with data. Of course, all of this is suggestive. They are not precise measurements, but they tell you that this framework is in the right ballpark. The other thing, of course, is that it says, unlike what everybody believed before, that relativistic hydrodynamics describing this expanding plasma would be valid 10 times earlier than people thought before. And indeed it is, now it's well established. Moreover, the viscosities are very close to the viscosities predicted by simpler models in holographic models, which are in fact the ultimate lower bounds of what viscosity can be in quantum field theories. In fact, there is a famous value that you may have heard, eta, which is the shear viscosity over 4 pi is equal to 1. That's what we believe is the ultimate bound for these types of theories. And the only other theories that come reasonably close is electrons in graphene, and there is also a strongly coupled Bose gas that has been constructed in experiments recently, but they approach this type of value. So these, of course, this is a story that goes on now for 20 years between theory and experiment. And I cannot do it justice in a few words, but that's the idea.
If there are other questions. Okay, are there other questions online? Nobody else, you see anyone? Nobody online? Okay, then let's thank Elias again. And as usual, we're having coffee, tea, and cookies, so you're all welcome to attend the discussion. Okay.